Hello everyone, in this video I am going to explain geometrical isomerism in alkenes. In previous video, geometrical isomerism in alkenes and cycloalkenes completed. And different notations for geometrical isomerism, different prefixes for geometrical isomerism. There are three different prefixes for geometrical isomers. Cis trans prefixes, EZ prefix and sin anti prefix. Among those three, two are completed. So in this video, I will explain geometrical isomerism in spiro compounds, geometrical isomerism in alkenes, geometrical isomerism in hydrogens, and geometrical isomerism in diazo compounds. I will explain cis trans prefixes also. First of all, geometrical isomerism in alkenes. What are alkenes? Alkenes are cumulative dienes. Alkenes are consecutive dienes. Consecutive dienes are cumulative dienes. Consecutive dienes are cumulative dienes. Diene means di means two, ene means double bond, two double bonds. So molecule containing two double bonds are dienes. Dienes are generally three types. They are cumulative dienes, conjugative dienes, isolated dienes. So dienes are three types. General information, dienes are three types. Cumulative dienes, these are also called as consecutive dienes. Conjugative dienes, and third one, isolated dienes. Dienes are how many types? Three types. Cumulative dienes, conjugative dienes and isolated dienes. In that first one, cumulated dienes. If double bonds are adjacent like this, cumulative dienes. These diene, two double bond, are called cumulative dienes. Cumulative dienes are consecutive dienes. If two double bonds are separated by a single bond, like this, double bond separated by single bond. Such dienes are called conjugative dienes. Third one, if two double bonds are separated by more than one single bond, such dienes are called isolated diene. Double bond, single bond, again single bond. Here two double bonds separated by more than one single bond, so it is called isolated diene. Thus dienes are how many types? Three types. Cumulative diene, or it is also called as consecutive diene. Second one, conjugative diene. Third one, isolated diene. Now I am talking about this one. Cumulative dienes or consecutive dienes are called alkenes. So alkenes show geometrical isomerism. If you understand the arrangement of atoms in alkenes, if it is carbon, consider thick line, it is present on right, and this bond present left carbon. Consider these two bonds like this, 1, 2, horizontally on this plane. Okay, next two bonds vertically. So about this horizontal bond, and this is vertical bond. Vertical double bond, sigma and pi bonds are vertical. Okay, here for horizontal, here hydrogen, here hydrogen. So for this bond trigonal planar sp2 carbon is double bond means sigma pi, sigma. How many sigma? 3 sigma. 3 sigma means sp2 hybridization. sp2 hybridization means trigonal planar shape. Trigonal planar shape here. So this is trigonal planar, like this. Okay, right here this is vertical, this is horizontal, like this. So horizontal, vertical. Double bond, this hydrogen here, double bond. Horizontal to this vertical, trigonal planar shape. Okay, here double bonds are like this. And two hydrogens are like this. So double bonds are vertical and hydrogens are horizontal, like this. Double bond is vertical, hydrogens are horizontal, like this. So here one hydrogen pointing towards observer, and one is away from observer, out of the board plane, like this. So this is another plane, like this. Here also trigonal planar shape. Okay, so this is sp2 carbon, this is also same sp2 carbon, trigonal planar shape. Here two hydrogens are like this. See this one, two hydrogens are like this, and two hydrogens are like this. Two hydrogens are like this, vertical, two hydrogens are horizontal. So then cis trans is not possible. Cis trans isomerism not possible. So if it is cis, if it comes down same distance, so cis trans isomerism possible. Cis trans isomerism possible only if all hydrogens are vertical, or all hydrogens are horizontal. Then only cis trans isomerism possible. But here these hydrogens are like this, and these two hydrogens are like this. So cis trans not possible. If like this, cis trans possible. Okay, right? So if you try to understand the orbital overlapping, here carbon, so I am writing one sp2 carbon, another sp2 carbon overlapped with hydrogen, and one sp2 carbon overlapped with sp2 carbon of another. This is another carbon. Here sp2 carbon, here sp2 carbon, hydrogen. Sorry, one more carbon here. This is sp, and this is also sp, and this is carbon, sp2, hydrogen here. Try to understand. Trigonal planar sp2, sp, sp2. sp2 means in carbon 2s subshell, 2p subshell. 2s subshell contain only one orbital, 2p subshell contain 3 orbital. sp hybridization means 2p orbitals are unhybrid. 2p orbitals are unhybrid. So sp hybridization means 2p orbitals are unhybrid. Here for this carbon sp2 hybridization. sp2 hybridization means one orbital is unhybrid. This is also same. sp2 carbon mean one s orbital is unhybrid. One s orbital is unhybrid, like this. Okay, so these two orbital overlap and form pi bond here. This is sigma and this is what? Pi bond. Here overlapping between these two are horizontal, like this. So this is pi bond and this is sigma bond. Try to understand, this is like this. Sigma and red is above the plane, like this. And here black bond sigma, pi is horizontal, like this. Okay, so for this hydrogens are vertical, or otherwise if you take this one to write that one, I am writing once again same shape. So this carbon vertical with carbon. So vertical carbon always contain horizontal hydrogen. So vertical bond means here horizontal, here horizontal hydrogen. So horizontal followed by vertical. So vertical followed by horizontal. This is pointing towards us, this plane, and this is back side. This is vertical bond, this is back side. Thick line towards us, carbon. So for horizontal, this is vertical bond, like this. This is allene. Horizontal, vertical, horizontal and vertical. See this horizontal, vertical cannot play geometrical isomerism. Horizontal can play, vertical can play geometrical isomerism, cis-trans isomerism. So in allenes, geometrical isomerism is not possible, even though 4 different groups may be present. 4 different groups here, R1, R2, same group, same side, you cannot say cis. For example, if it is hydrogen, or is it hydrogen, this is chlorine, or this is chlorine or something, any. So 2 hydrogen same sides is wrong. 2 hydrogen not same side, 1 hydrogen horizontal plane, one hydrogen vertical plane, not same side. If this hydrogen comes down, then also not possible. So whenever double bonded dienes in allenes, geometrical isomerism is not possible. My final statement, geometrical isomerism is not possible in conjugative dienes. In trienes possible. I will show. In cumulative dienes, geometrical isomerism not possible. Okay, take this one, I will explain. For trienes, this is vertical bond, this is horizontal bond. For trienes, vertical bond, horizontal bond, vertical bond. For vertical, hydrogens are horizontal. For vertical, this is horizontal. See, this is horizontal pointing us towards us like this, thick line towards us, black line away from us like this. Okay, black. So horizontal followed by vertical, followed by horizontal, followed by vertical, followed by horizontal. Two horizontal can play geometrical isomerism. Geometrical isomerism possible. So these two groups present same side cis. If these two are take any other like Dr, for example chlorine, I take chlorine, cis trans isomerism possible. So for example, if you write like this is hydrogen and this is chlorine, vertical bond followed by horizontal bond, this is horizontal bond, okay. Next followed by vertical bond, again horizontal. If you write hydrogen here and chlorine on this one, chlorine, so this become what? Two chlorines on this thick line above the plane, this is below the plane, or this is towards us, this is away from us. Same side, cis. Two chlorines opposite side, trans. Therefore, in trienes, geometrical isomerism possible. Geometrical isomerism possible. This is somewhat advanced class. Geometrical isomerism is possible. In the similar way, geometrical isomerism in spiro compounds. I will explain geometrical isomerism. It is similar to above one. Geometrical isomerism in spiro compounds. What are spiro compounds? Bicyclo compound having sp3 carbon bridge, tertiary carbon bridge, like this. Vertical, because this is sp3 carbon. sp3 carbon has sp3 carbon which shape? Tetrahedral. Tetrahedral means all the 4 bonds not present on the board. sp3 is tetrahedral shape. Tetrahedral shape is not planar. So tetrahedral shape is not planar. If these two are vertical, then these two become horizontal, like this. Like this. This is vertical and this is horizontal, like this. Now here hydrogen, here hydrogen, here hydrogen, here hydrogen, or anything. So or say something R1, R2, R1, R2, R1, R2, R1, R2. Geometrical isomerism possible or not? R1, R1 same side. Is it same side? No, this is not same side. So these two are vertical. This is vertical. R1, R2 arranged vertical line. Sorry. So for this to that vertical line, R1, R2 are horizontal, like this. This is R2. Say this is R1. Are these two same side? No. These two are not same side. So this is like this, this one, my point finger, and this is like this, my point finger. Point finger, same side. Can you say same side? Opposite side? No. If like this, 2 point finger same side is 2 point fingers opposite side trans. But one is vertical, other is horizontal. Cis trans not possible. So this is vertical and this is horizontal, and this is vertical, this is horizontal, this is vertical. Horizontal, vertical cannot play geometrical isomerism. If 3 such cycles are present, geometrical isomerism possible. Yes. Here GI, geometrical isomerism, not possible. Geometrical isomerism not possible. If three of such cycles are present like this, vertical, horizontal, again vertical, to these hydrogens are horizontal or groups are horizontal, R1, R2. Okay, because all these carbons are sp3 carbon, you have to write two vertical, two horizontal. All are if all you write vertical, that means that becomes square planar shape, but sp3 carbon doesn't contain square planar shape, it has tetrahedral shape. For tetrahedral, two horizontal, two vertical. If you write all vertical, that becomes square planar shape. Remember, sp3 carbon is not square planar. So vertical means here horizontal. Hydrogen comes here, R1, R2, like this. So see here, this is what? Horizontal, vertical, horizontal, this is vertical, again horizontal, horizontal, horizontal. Geometrical isomerism possible. So 2 cycles not possible, 3 cycles possible. 2 double bonds not possible, 3 double bonds possible. In trials possible. Cumulative triins, geometrical isomerism possible. So here GI possible, GI possible, GI possible. Okay, somewhat advanced. Okay, next geometrical isomerism in aldaxymes, ketoxymes, in which I explain syn anti notation also. Take this one. I am giving all concepts, basic concepts of organic chemistry in series of videos. So note down all my classes, take a notes, write a notes. If you read twice or thrice, you can better understand organic chemistry. Okay, all basics, I am not leaving anything. I am covering all the things in a series of videos. So watch from beginning first organic chemistry video. It helps you a lot. Okay, next geometrical isomerism in aldaxymes. Geometrical isomerism in aldaxymes. How will aldaxymes are formed? When aldehydes RCHO treated with hydroxylamine NH2OH. This is what aldehyde. RCHO is aldehyde. NH2OH is hydroxylamine. Its name is hydroxyl. OH group. Amine NH2 group is present. That's why amine. So in acidic medium, what happens? Here remove these two and write RCH between carbon and nitrogen double bond and nitrogen here. This is called aldaxyme. Aldaxymes show geometrical isomerism. Aldaxymes show geometrical isomerism. How? Because of lone pair electron present on nitrogen. Nitrogen 3 bonds means lone pair is there. Okay, if you write like this, when H and OH present of aldaxyme, present on same side, these two are not similar. Hydrogen OH are not similar. You cannot say these two are cis. It is a special word. It is said to be, it is syn isomer. Syn and anti concept here, syn isomer. When HOH of aldaxams present on opposite side, it is called anti-isomer. Syn isomer, anti-isomer. See this, if R, I am writing R here, and carbon, to the carbon hydrogen, carbon double bonded with nitrogen, or carbon H, to carbon double bond nitrogen, and nitrogen contain OH and lone pair also. Same side, syn. If you write like this, your nitrogen, OH left, lone pair like this. Both are opposite side, anti. Same side, HOH same side, syn, HOH opposite side, anti, syn and anti. Okay, this is third prefix, third type of notation. Take this one. Next, geometrical isomerism in ketoxames. How much time? 26 minutes. Okay, we are free. Geometrical isomerism in ketoxames. This is aldaxame. Next, ketoxames. Ketones, when treated with hydroxylamine, ketones form ketoxames. Ketones with hydroxylamine, they form ketoxames. Ketone, R, C, double bond O, R. Ketone. So one is R, other is R prime, like this. Geometrical isomerism in ketoxames. Geometrical isomerism in ketoxames. When ketone treated with ketones, treated with NH2H, hydroxylamine. When ketones treated with hydroxylamine in acidic medium. Okay, so remove H and H2O, then it give R, C, R prime, double bond NOH. Nitrogen contain lone pair. This is called ketoxame. For aldaxame, here hydrogen. For aldehyde, here hydrogen, RCHO. For ketone, RC double bond O, R. So two alkyl groups. In aldaxames, one R, one H. In ketoxames, both are R. Ketoxames show geometrical isomerism. Ketoxames show geometrical isomerism. Okay, if high priority groups present on same side, just like EZ configuration, priority selection rule for priority of groups, CIP rules, they are also said to be CIP rules. If high priority groups present on same side, it is called high priority groups present on same side, it is called syn. If high priority groups present on opposite side, it is called trans. Use prefix trans. Syn anti, not trans. Syn anti. For example, if you take like this example, methyl group CH3, here ethyl group C2H5, ethyl group double bond N, one lone pair, one is OH group. So nitrogen with lone pair, yes, your lone pair. So between lone pair and OH group high priority, methyl and ethyl. So in methyl and ethyl is what? CH2, CH3, total C2H5. So here carbon leave it, 3 hydrogen, after 2 hydrogen here again carbon. So first atom carbon, first one carbon, second one hydrogen, third one again hydrogen, fourth one also hydrogen, fourth atom hydrogen. Here this group is like this, CH2, CH3. First atom carbon, second atom hydrogen, third atom hydrogen, fourth atom again carbon. So this one differentiate. Fourth atom hydrogen, fourth atom carbon. High priority. High priority groups, high priority. Here this one high priority. High priority groups same side. High priority group same side. What do you say? Syn. So this is what? Syn ketoxide. High priority groups same side, syn ketoxide. If you write opposite like this, CH3 here, C2H5 ethyl group, double bond N, lone pair down and OH group up. High priority groups here, ethyl group, OH group opposite side. This is what? Anti-ketoxide. Syn ketoxide, anti-ketoxide, like this. In the similar way, syn anti-notation, geometrical isomerism in hydrogens. Take this one. Geometrical isomerism in hydrogens. I will explain geometrical isomerism in hydrogens. Geometrical isomerism in hydrogens. What are hydrogens? How will they form? Hydrogens. When carbonyl compound, that may be aldehyde or ketone. Carbonyl compound. Carbonyl, what is carbonyl compound? Aldehydes or ketone, anything not assigned. Here RH, aldehyde, RR, ketone. Aldehydes and ketones collectively said to be carbonyl compounds. Aldehydes and ketones collectively said to be carbonyl compounds. When carbonyl compound is treated with NH2. Okay, here removal of this one. Reaction is not important, just I want to explain what is hydrogen. So this is hydrogen. When carbonyl compounds treated with hydrogen, they form corresponding hydrogen. So here these groups may be anything. Double bond N, NH2. The nitrogen lone pair are there? Yes, lone pair. Therefore, geometrical isomerism possible. So, see one example. Hydrogens show geometrical isomerism whenever sp2 carbon contain different alkyl group. Hydrogens show geometrical isomerism if they have carbonyl carbon if carbonyl carbon contain two different groups, one hydrogen, one alkyl, or two different alkyl, one alkyl, one hydrogen, or maybe two different alkyl, anything, or so here H double bond N lone pair, here NH2. Okay, high priority group. So CH3 beginning with carbon, this is hydrogen. Definitely this is high priority, this is high priority. Opposite side, anti-isomer. If you write like this, nitrogen NH2 up and lone pair down, your alkyl group same, your hydrogen same, high priority between hydrogen and carbon, high priority carbon. Between lone pair and nitrogen. So high priority groups to same side, syn isomer, syn. Not only simple hydrogen, phenyl hydrogens also show geometrical isomerism, same. So here instead of one hydrogen, pH comes here, phenyl group instead of one. So that phenyl group doesn't make any difference with hydrogen. Phenyl hydrogen both are same. In point of geometrical isomerism, phenyl hydrogens just hydrogens same. So phenyl group doesn't make any difference. So hydrogens show geometrical isomerism. That's my point. And finally, only one thing, geometrical isomerism in last one, geometrical isomerism in azo compounds. Geometrical isomerism in azo compounds. Azo compounds means nitrogen double bond nitrogen. So like this. Azo compounds means like this. N bond N. This is diazo compound. Diazo compound or azo compound. Geometrical isomerism possible because lone pairs. How do you write? So write pH here. This is phenyl group, or simply pH. Your lone pair, double bond nitrogen, lone pair here, phenyl group pH. Same side, two high priority groups same side, syn. If you write phenyl group up, lone pair, phenyl group here lone pair. Phenyl groups opposite side, anti, syn and anti. Okay, thus geometrical isomerism shown by azo compounds also. So I will write that point. Diazo compounds, azo compound or diazo compound both are same. Diazo compounds show geometrical isomerism. Geometrical isomerism. Okay, hope you understood well. In next video I will explain optical isomerism. With optical isomerism topic will complete. Okay, thank you. Take this one.